All right, everyone, I'm going to be talking about Lab 6, which is on lenses. This one has like an extremely long introduction to the lab, unfortunately. But how the lab starts off is they say that when we're looking at like light rays that pass through like something that's flat, they don't change direction, and that's it. So like if I have something like this, it doesn't change direction because this thing is flat. All right, it's flat, doesn't change direction. That's all it is. that's that's it. And then they go ahead and they define something called a near focal point and a far focal point. Okay, and so all they're saying is that like every lens, like I just say the lens looks like this, like it's gonna have some near focal point and it's gonna have some far focal point where the light focuses on that point. Um, and so that's really all it is. And then also they just note that these distances are like identical. So if this is D, then this is also D. Okay. And so the first type of lens they talk about is a converging lens, which is looks like this, where it bows outwards. The reason they call it a converging lens is because when you pass light parallel to the lens, the light will converge onto the far focal point like this. And then if you put it outwards, um, essentially in the opposite direction, like if you were to reverse this far, um, if we were to have this far point in, like if you were to put the waves like this, then then they would come out parallel. So they would just be moving in the opposite direction essentially. And then the next type of wave, or next wave, not wave, the next type of lens is a diverging lens where you put it through on this side and it diverges away from the focal point. Okay? And then you can obviously do this in reverse and you get the same thing. Okay? And so then they talk about the three types of rays, which are, or like the three types of rays that we like think about a lot, which they call the principal rays. So the first principal ray is just a ray that passes through um, the center. And so if you look at the center, like if you were to zoom in, like it looks flat. These two things look flat, and we said in the beginning that if we put a light ray through something flat, then we end up with no distortion. And so that would be the first principal ray. And then the second principal ray is one that comes from the object parallel to the center axis of the lens. So like this would be the lens, so parallel to the center axis of the lens. And so essentially it's just something that comes in parallel to the lens. That's like really all it is. And for a converging lens we looked at earlier, it'll just do that. But for a diverging lens, we said that it'll refract off like this. And then we get something called a virtual ray. So like if you were to put your eye here, like to your eye, it just looks like this ray just essentially like it looks like there was something flat here, and then the ray just like passed through it. Like to your eye, that's what it looks like. And so they call it a virtual ray because this isn't like the actual ray of light that existed, but that's what your eye perceives it as. And then the last principal ray is tracing a light ray from the object that will eventually leave the lens parallel. So for a converging lens, if we pass through the focal point, we'll end up leaving parallel. And so that would be the what's the word? That would be the third principal ray. Sorry. And then for a diverging lens, so this is a converging lens or a convex, and then this is a diverging lens or a concave lens. You can think of concave as like something concave is just like sunken inwards. So that's how I remember it. And then again here we pass it through at an angle, and then it ends up being parallel. All right. And then the virtual ray would be like this, because if you put your eye here, it just looks like the ray was just passing straight through. All right. And then they go through and they tell you that there's this equation that exists. And so this equation just lets you say, if you know the focal point, and then you know S and S prime, which are the distance from the object to the lens, and then the distance from the lens to the image, respectively. if you know those two, or not those two, if you know like any two of them here, you can calculate the other, and that's great. And so just keep in mind that like S and S prime can be positive or negative, depending on which side of the lens you're on. So I would honestly say you should just memorize this, but if you prefer to like think about it sort of logically and come up with it during an exam, that's also okay. The next thing they talk about is like a magnification. So essentially, like, let's just say we had like some image, and then went through like, I don't know, some lens or whatever, and then like the image ended up like looking like this or something, or maybe like this. Then we can see that this looks bigger than this, so it had like a magnification, like the absolute value at least was like greater than 1. And then if the image is inverted like this, it would be negative. So I guess we would have like m would be, like in this example that I drew, like m would be less than 0, meaning m would be negative. And so magnification is just how much bigger or smaller, as like a fraction or a ratio, an image looks. And so the next part of the lab sort of walks through an example where we calculate the where we like calculate the magnification and stuff for an object, or like they walk through how you would like draw out the object and image over time. So this first part tells you what happens after you go through this first lens, and then the second part says that we use the object that we just got out of that first lens to look at how it passes through the second lens, and then this is like our final image, which is upright. So this would be like a positive magnification. All right. And so then the first part of the lab is like just a bunch of examples of like determining where images will form for 1.1, and then you talk about when you have a real versus a virtual image, a magnified image, and then you complete ray tracings for this next part. So like a lot of it's a lot of drawing, and then the actual first part of like the real experimental part of the lab is you looking at is you taking so I don't know if they show it here, but like essentially you have like an apparatus where like we have light coming out of here, and then it's like on a rail, and then we have like a wall at the end, and then you can set up lenses wherever you want. I'll just call it L for light, and then so like the light passes through the lenses, whatever, gets diffracted, all refracted, all that stuff. Not diffracted. That was last lab. All right. So for the first like part of the lab, you're going to work with a single converging lens. And remember, a converging lens looks like this, or it's a convex lens. And then you can read through this, like it just walks you through what to do. You're going to place like you're going to choose the 100 millimeter plus 100 millimeter focal length lens, which they're labeled on the lenses. So don't worry about that. You're going to place it. You're going to record like the object distance, image distance, size of the image, a bunch of stuff in a table. You're going to repeat the experiment for different focal length lenses, and then you're just going to see if there's any relationships. And then for part 3, you're going to place the 100 millimeter focal length lens again, but at a distance of 0.25 meters from the light source this time. You're going to use the thin lens equation, which is like 1 over s plus 1 over s prime equals 1 over f. That's the thin lens equation. Remember, f is the focal length. And you're going to calculate where the image will form, and then you're going to place your screen at that location just to see if that turned out to be true, that the image formed there. And you're going to be calculating the magnification again. You're going to be doing a bunch of calculations for all this stuff, and seeing if the data you're getting matches the calculations you're expecting, or like the theoretical locations of the images and the magnifications and stuff like that. And then the last part of the lab is about a real image of a virtual object. So sometimes you can have a virtual object if you have like a multiple lens system. And so that means, they tell you here that in order for there to be a virtual object, the object has to be in the back of the second lens. And then they go on to explain more, like it's the same side where it's the same side where the light ends up, again, you're gonna do this experiment. It walks you through what to do. You're gonna be placing a plus 200 millimeter focal length lens at a certain distance, and then you're going to use the thin lens equation, calculate the image distance to where the image will form. You're going to place the screen wherever it needs to go, and then I mean, it walks you through it. I'm not gonna go too much into it, but there actually is no like conclusion for this lab, given that this lab is uh seems to be quite long. But I mean, you guys will be able to uh figure it out. But um, thank you for watching. I know this one was a little longer, but this lab manual is like absurdly long, so hopefully it wasn't too bad. But thank you.